Welcome to Scientific Serenity. Tonight, we close our eyes and travel not outward, but inward, into the most profound prediction of the human mind, into a darkness so complete it swallows light, into the story of an idea so radical it took half a century to become real. This is the story of the black hole. But before there were images, before there were signals, even before there was a name, there was a thought, a simple, terrifying, beautiful thought. What if gravity could win? Our story begins not with telescopes, but with minds, with the universal law of gravitation proposed by Isaac Newton in 1687. Newton's equations described a force that acted instantly across space, tying the moon to the earth, the planets to the sun. They introduced a critical concept, escape velocity. To break free from a planet's gravitational grip, an object must achieve a certain speed. For Earth, that speed is about 11 kilometers per second. But Newton's mind did not stop there. He pondered a deeper question. If a celestial body were massive enough, or compact enough, its escape velocity could exceed the speed of light. What then? In Newton's world of corpuscular light, made of particles, he speculated that light itself could be pulled back down. He wrote of stars so massive that no light could escape from them. He called them dark stars. It was a speculative footnote, a curiosity in the margin of his great work. For over a century, it remained just that, philosophical musing. The idea lay dormant until 1783, when an English natural philosopher named John Michell, rector of Thornhill and a brilliant thinker, picked up the thread. Michell, using Newton's own laws, performed a calculation. He considered a star with the same density as the sun, but with a radius 500 times larger. Its surface gravity, he found, would be so immense that the escape velocity would exceed the speed of light. Therefore, he reasoned, such a star would be invisible. All light emitted from its surface would fall back, pulled by its own gravity. Michell called these objects dark stars. He even proposed a method to detect them, by observing the gravitational influence they exerted on nearby visible stars. It was a stunning theoretical leap, the first concrete model of a light-trapping object. But Michell's work was published in the Philosophical Transactions of the Royal Society and was largely forgotten. The world was not ready for invisible stars. The 19th century passed without serious consideration of dark stars. Light was now understood as a wave, not a particle, and it was unclear how gravity could affect a wave. The Newtonian framework offered no mechanism. The idea faded into obscurity, a forgotten ghost in the attic of physics. Then came the earthquake. In 1905, a young patent clerk in Bern, Switzerland, named Albert Einstein, published his theory of special relativity. Its central postulate, the speed of light in a vacuum is constant and absolute, the ultimate speed limit of the universe. Nothing with mass could ever reach it, let alone exceed it. This seemed to slam the door forever on Newton's and Michell's dark stars. If nothing could go faster than light, and light could not escape, then the dark star itself was impossible, a logical contradiction. But Einstein was not finished. For the next decade, he wrestled with a grander vision, one that would fuse gravity with his new relativity. The result, published in November 1915, was the general theory of relativity. This was not a correction of Newton, it was a revolution. Gravity was not a force, Einstein proposed, but a curvature of space-time itself. Mass and energy told space-time how to curve. Curved space-time told matter how to move. The sun's mass created a depression in the fabric of the cosmos, and the planets rolled around that depression like marbles in a bowl. It was a geometric theory of gravity, expressed in a set of complex field equations. The implications were profound and dizzying. One immediate prediction was the bending of light by gravity. If space-time was curved, then light, traveling along the shortest path, a geodesic, would also bend as it passed a massive object. This was a radical departure from Newton. Einstein's equations were a new language for the cosmos. The task now was to solve these equations for specific situations. While Europe was engulfed in the trenches of the First World War, a German physicist and astronomer named Karl Schwarzschild, serving on the Russian front, found a solution. Despite the chaos around him, he obtained a copy of Einstein's paper. In the brutal cold of the Eastern Front, between calculating artillery trajectories, Schwarzschild solved Einstein's field equations for the gravitational field around a single, non-rotating, spherical mass. He sent his solution to Einstein in a letter. Einstein was astonished. He presented Schwarzschild's work to the Prussian Academy of Sciences in Berlin in January 1916. The solution was elegant, but it contained something peculiar, a mathematical singularity at a certain distance from the center of the mass. This distance, now known as the Schwarzschild radius, marks the point of no return. For an object compressed within this radius, the curvature of space-time becomes infinite. The escape velocity equals the speed of light. Schwarzschild had, unknowingly, mathematically described the boundary of a black hole. He called it a coordinate singularity, a mathematical artifact. Tragically, he died months later from an autoimmune disease contracted at the front, never knowing the true magnitude of what he had uncovered. Einstein himself grappled with this result. He believed it was a mathematical curiosity with no physical relevance. He could not conceive of nature actually crushing matter to such an extreme density. In his mind, some physical process would always intervene to prevent such a collapse. For him, the Schwarzschild solution described a ghost, a mathematical phantom that could not exist in the real universe. He published papers arguing against the physical possibility of what we now call a black hole. Thus, by 1920, the situation was a profound irony. The equations of the greatest theory of gravity ever devised contained the blueprint for the most extreme object in the universe. Yet the theory's own creator, and most of the scientific community, dismissed it as a fantasy. The dark star had been reborn in the language of curved spacetime, but it was still a ghost, waiting for its time to become flesh. And as you listen now, consider the weight of that idea, born in war and nurtured in skepticism. It was an answer waiting for a question, a shadow waiting for a light to cast it. The universe held this secret, and the human mind had already glimpsed it, only to look away. The dissonance between the mathematical elegance of general relativity and the physical rejection of its most extreme prediction created a silent tension in astrophysics. For years, Schwarzschild's solution was a textbook footnote, a curious boundary where physics broke down. But science, especially theoretical physics, is driven by minds unwilling to accept such breakdowns as final. They see them instead as doors. One such mind belonged to a young Indian physicist named Subramanian Chandrasekhar. In 1930, at the age of 19, he embarked on a long sea voyage from India to England to begin graduate studies at Cambridge. During the journey, with nothing but the ocean and the stars, he contemplated the fate of white dwarfs. These are the dense, Earth-sized cores left behind when a star like the Sun exhausts its nuclear fuel. They are supported against further collapse by a quantum mechanical pressure known as electron degeneracy pressure. Chandrasekhar performed a revolutionary calculation. He asked, what happens if the mass of the stellar remnant is too great for this quantum pressure to withstand? He found a critical threshold. If the core of a dying star exceeded about 1.4 times the mass of our Sun, electron degeneracy pressure would fail. Nothing could stop its gravitational collapse. This value, now known as the Chandrasekhar limit, implied a startling destiny for massive stars. They would not peacefully become white dwarfs. They would keep collapsing indefinitely. When Chandrasekhar presented his findings at the Royal Astronomical Society in London, he faced immediate and fierce opposition. The great astrophysicist Sir Arthur Eddington, who had championed Einstein's work, publicly ridiculed the idea. He argued that nature would find a way to avoid such a ridiculous outcome. A star could not just vanish into a point of infinite density. Eddington's authority was immense, and Chandrasekhar, a soft-spoken young foreigner, was crushed. He eventually turned to other areas of astrophysics. His limit accepted, but its ultimate consequence ignored for decades. Yet the theoretical problem would not die. If a star's core surpassed the Chandrasekhar limit, what was the end point? The question found its most serious investigators in the late 1930s on the other side of the Atlantic. Robert Oppenheimer, who would later become known as the father of the atomic bomb, and his graduate student Hartland Snyder, took up the challenge. They decided to follow the mathematics of general relativity to its ultimate, brutal conclusion. In 1939, they published a seminal paper titled On Continued Gravitational Contraction. They considered an idealized, spherical cloud of dust with no internal pressure. Using Einstein's equations, they traced its collapse. Their results were stark and inescapable. The cloud would shrink, its surface gravity would increase. The light rays emitted from it would become redder and dimmer as they fought the growing curvature of space-time. Eventually, the cloud would reach its Schwarzschild radius. At that point, time itself, for an outside observer, would appear to freeze. The collapsing star would fade from view, leaving behind only its gravitational field, a perfect, dark, spherical tomb in space. Oppenheimer and Snyder had provided the first rigorous description of the formation of what we would call a black hole. They wrote, "The star thus tends to close itself off from any communication with a distant observer." It was a momentous paper, but its timing was catastrophic. It was published in September 1939, the same month Hitler invaded Poland and World War II began. The world's attention, and that of its physicists, turned to uranium fission and radar. The paper on gravitational collapse was filed away, another ghost lost in the tumult of history. The war ended, leaving a new world and a new physics born in the fires of Los Alamos. Oppenheimer was a changed man, haunted by the destructive power he had helped unleash. He showed little interest in returning to the esoteric problem of collapsing stars. For nearly 2 decades, the subject languished in a scientific purgatory. It was considered a fringe topic, the province of mathematicians and relativists playing with extreme solutions, with no connection to the real universe observed by astronomers. The rebirth began in the late 1950s and early 1960s, driven by 2 forces: the rise of computational power and the dawn of the space age. With new electronic computers, scientists could finally simulate the complex, non-spherical collapse of a real star. They discovered something remarkable. The Schwarzschild singularity was not a mathematical artifact to be avoided. It was a generic, stable outcome. Unless a star shed enormous amounts of mass, a sufficiently heavy core would inevitably collapse. Beyond the point of no return, the pivotal figure emerged to give this object a name and a place in the scientific lexicon: John Archibald Wheeler, a charismatic and forceful physicist at Princeton. Wheeler was a master of vivid language. He understood that an idea without a compelling name was an orphan. For years, the object had been called a frozen star, collapsed star, or referred to awkwardly as a Schwarzschild singularity. In 1967, during a conference, Wheeler grew tired of the clumsy phrases. He declared that these objects needed a name that captured their essence. He reportedly said, "They are black. They are holes into which things can fall, but from which nothing can escape." And so, the term black hole was born. It was simple, memorable, and perfectly evocative. Wheeler popularized it relentlessly, in lectures and writings. The name stuck, and with it, the object gained new legitimacy. It was no longer a mathematical oddity. It was a black hole, a potential resident of the real cosmos. Now, the theoretical groundwork was complete. The equations of general relativity, pioneered by Einstein, solved by Schwarzschild, and explored by Oppenheimer and Chandrasekhar, had converged on a stunning prediction. Massive dying stars could leave behind corpses of pure gravity, regions of space-time curved so severely that they severed themselves from the universe. The ghost had a name. The next step was the most difficult of all, finding one. With the theoretical existence of black holes firmly established and a powerful name bestowed upon them, the quest entered a new and pragmatic phase. The ghost had been given form in the equations. Now science demanded evidence. How do you find an object that, by its very definition, emits no light? You look for the wreckage it leaves in its wake, for the screams of space-time it creates, for the shadow it casts against the bright backdrop of the universe. The hunt for the invisible began. The first strategy was indirect, a method prefigured by John Michell himself 2 centuries earlier. A black hole may be dark, but its gravitational pull is omnipotent. If it exists in a binary system, locked in a gravitational dance with a normal, luminous star, it will betray itself. The visible star will orbit an unseen companion. By applying Newton's and Kepler's laws to the wobble of the visible star, astronomers could calculate the mass of its invisible partner. If that calculated mass exceeded the theoretical limit for a neutron star, the only other conceivable compact object, then the dark companion could only be one thing: a black hole. The perfect hunting ground for such a system emerged with the birth of X-ray astronomy. Earth's atmosphere blocks X-rays from space, so this new window on the universe only opened with the launch of rockets and satellites in the 1960s. Scientists discovered that the cosmos was filled with powerful, variable X-ray sources. One of the brightest was in the constellation Cygnus, dubbed Cygnus X1. In 1971, radio astronomers pinpointed the location of Cygnus X1. It coincided with a bright blue supergiant star named HD 226868. Observations soon revealed that this massive star was indeed part of a binary system, whirling around an unseen companion every 5.6 days. The calculations of the unseen object's mass were conclusive. It was at least 9 times the mass of our Sun, far beyond the maximum possible mass for a neutron star. The companion had to be a black hole. Here was the drama. The black hole's immense gravity was tearing gas away from its gigantic stellar partner. This stolen gas did not fall directly into the abyss. Instead, it formed a vast, swirling, superheated disk around the black hole, an accretion disk. Friction within this disk of doomed matter heated it to millions of degrees, causing it to glow fiercely in X-rays before it spiraled past the event horizon, vanishing from our universe. Cygnus X1 was not a silent tomb. It was a cosmic crime scene, illuminated by the last screams of its victim in the X-ray part of the spectrum. The announcement sent ripples through the scientific community and the public. Stephen Hawking, who had been working on the theoretical properties of black holes, famously made a bet with fellow physicist Kip Thorne in 1974, wagering that Cygnus X one was not a black hole. It was a playful expression of the healthy skepticism required in science. Hawking would later concede the bet in 1990, when the evidence became overwhelming. The ghost had been sighted, not by seeing it, but by seeing the violent whirlpool of light around its maw. The discovery of Cygnus X, one transformed black holes from mathematical ghosts into astrophysical realities. It launched a new field of observational black hole physics. Astronomers began searching for and finding other stellar mass black holes in our galaxy through their X-ray signatures and their gravitational influence on companion stars. But a grander vision was already taking shape. If dying stars could leave behind black holes a few times the mass of the sun, what about the corpses of much larger events? In the hearts of most galaxies, including our own Milky Way, astronomers suspected something far more monstrous resided. The motions of stars at the galactic center were frantic, suggesting they were orbiting an immense, compact mass of millions, even billions of solar masses. This could not be explained by a dense cluster of normal stars or neutron stars. The only plausible explanation was a supermassive black hole, our own galactic center. A region called Sagittarius A** became the prime target. For decades, astronomers tracked the orbits of individual stars near this invisible focus. Their paths were precise, swift ellipses, following Kepler's laws around a dark central mass. By the early 21st century, the data was unequivocal. The stars were orbiting an object with a mass of over 4 million suns, confined to a region smaller than our solar system. The only entity that could pack such mass into such a small volume was a supermassive black hole. The ghost was not just a stellar phenomenon. It was an architectural cornerstone of galaxies themselves. The journey from Michel's dark star to the confirmed monster at the heart of our galaxy represents one of the great triumphs of the scientific method. It was a journey from pure thought, through mathematical prophecy, to indirect detection. It validated the power of human reason to penetrate the deepest secrets of the cosmos, to believe in the existence of things that could not be seen, because their effects could be measured. As you listen now, let the scale of this intellectual adventure settle upon you. It began with a question about escape velocity, was encoded in the geometry of space-time by a scientist at war, was resisted by its own creator, was named by a wordsmith, and was finally cornered by watching the death spiral of hot gas and the frantic dance of distant stars. We had mapped the shadow by the behavior of the light around it. This is where our first chapter ends. We have moved from imagination to inference, but a deeper desire remained, to see the unseeable itself, not just its effects, to move from inference to image. That required a telescope the size of the earth, and a willingness to look into the heart of darkness. That story belongs to another night. For now, rest with the knowledge that the universe contains these perfect paradoxes, objects defined by their absence, prisons of gravity born from the death of light, whose discovery crowned a century of human curiosity. They are out there, and we found them. The confirmation of Cygnus X, one was a watershed, but it was the culmination of a path paved with stubborn calculations, fierce debates, and a fundamental reimagining of stellar death. The black hole was no longer just a solution to Einstein's equations. It was a physical destiny waiting in the heart of massive stars. This chapter is the story of that destiny, of how theorists pieced together the final moments of a giant star and predicted the birth of darkness. Our story returns to the fate of matter under extreme pressure. The work of Subramanian Chandrasekhar had established a limit, but it was a limit for white dwarfs supported by electron degeneracy pressure. What if a star's core was even heavier? In 1932, the discovery of the neutron provided a tantalizing hint. Perhaps a star could collapse further, until protons and electrons were crushed together to form neutrons, creating a city-sized ball of nuclear matter so dense that a teaspoonful would weigh billions of tons. This was the neutron star. In 1934, Walter Baade and Fritz Zwicky proposed the existence of neutron stars, linking them theorically to the violent explosions known as supernovae. They suggested a supernova represented the transition of an ordinary star into a neutron star. It was a brilliant insight, but the neutron star itself remained a theoretical construct, seemingly as fantastical as the black hole. The crucial question of stability remained. Was there maximum mass for a neutron star, just as there was for a white dwarf? Robert Oppenheimer and his student George Volkoff took up this challenge. In 1939, building on the work of Richard Tolman, they applied general relativity to a simplified model of a neutron star, a sphere of pure neutron gas. They found the Oppenheimer-Volkoff limit. Beyond a certain mass, estimated around 2 to 3 solar masses, not even the nuclear forces between neutrons could withstand the crush of gravity. For a core remnant above this limit, the collapse would not stop at the neutron star stage. It would continue. This was the direct precursor to the work Oppenheimer would publish with Hartland Snyder later that same year on continued gravitational contraction. The sequence was becoming clear. A dying star's fate was a cosmic scale, weighed by mass. A star like our sun would become a white dwarf. A more massive star would explode as a supernova, leaving behind a neutron star. But the most massive stars of all, those with cores surpassing the Tolman-Oppenheimer-Volkoff limit, would face a different end. After the supernova blast, the remaining core would have no equilibrium state. No known force in the universe could arrest its fall. The mathematics of the Oppenheimer-Snyder paper described this fall with chilling clarity. They depicted a star not as a rigid object, but as a cloud of pressureless dust particles, all starting from rest at the same moment. Under its own gravity, every particle would accelerate inward. The collapse would be uniform and total. To an observer riding on the surface of this collapsing star, the journey to the central singularity would take a finite, brief amount of time. but to a distant astronomer watching through a telescope, a profound relativistic effect would take hold. As the star's surface approached the critical Schwarzschild radius, the gravitational redshift would become infinite. The last photon emitted from the surface would be stretched to an infinitely long wavelength, carrying zero energy. The star would not explode or flash. It would simply fade from view, reddening into darkness. Its clock, as seen from afar, would appear to slow to a halt. The star would freeze at the threshold, forming a perfect, static, dark sphere, the event horizon. For all practical purposes, the star would have vanished from the observable universe, leaving behind only its gravitational imprint. This was the theory. But in the aftermath of World War II, the physics community was fractured and its priorities lay elsewhere. Nuclear physics and particle accelerators were the frontiers. Relativity and cosmology were considered classical, even passé. The work of Oppenheimer and Snyder, and the critical mass limits of Chandrasekhar and Volkoff, gathered dust. They were seen as beautiful mathematical exercises concerning objects too bizarre to exist in nature. The revival began in the late 1950s, fueled by two developments. First was the dawn of the computer age, solving the full, nonlinear equations of general relativity for a realistic, non-spherical, rotating collapsing star was impossible by pen and paper. But with early digital computers, it became a tractable, if monumental, challenge. Pioneers like Martin Kruskal, John Singh, and David Finkelstein began re-examining the Schwarzschild solution, peeling away the misleading coordinates to reveal the true, dynamic geometry of what we now call a black hole. They showed the event horizon was not a physical barrier or a frozen surface, but a one-way membrane in space-time. Things could fall in, but nothing could come out. The second development was the rise of radio and X-ray astronomy, revealing a universe far more violent and energetic than anyone had imagined. Quasars were discovered, incredibly bright, point-like objects at vast distances, pouring out the energy of 100 galaxies from a region no larger than our solar system. What engine could possibly power them? Theorists like Yakov Zeldovich in the USSR and Edwin Salpeter in the US independently hit upon the same idea in 1964. The only conceivable power source was gravitational energy, released by matter spiraling into a supermassive black hole, weighing millions or billions of suns. The black hole was no longer just a corpse. It was a possible engine of cosmic brilliance. This confluence of theoretical refinement and startling observation created a ferment. The black hole idea began to escape the confines of relativity seminars and infiltrate mainstream astrophysics. It needed a spokesman, a champion who could synthesize the ideas and sell them to the wider community. That champion was John Archibald Wheeler. Wheeler was a force of nature. At Princeton, he had mentored Richard Feynman and had been a key figure in the development of the hydrogen bomb. He possessed a deep physical intuition and a flair for the dramatic. In the mid-1960s, He turned his formidable energy to the problem of gravitational collapse. He organized conferences, gathered the leading minds, and hammered away at the remaining objections. He argued that the black hole was not a pathological exception, but a generic, stable, and inevitable endpoint for massive matter, and he gave it the name that stuck. Before Wheeler, physicists used clumsy phrases like completely collapsed gravitational object or Schwarzschild singularity. During a talk at the Goddard Institute in New York in 1967, Wheeler recounts that he grew tired of the jargon. He said, "The black hole has no hair." This phrase, meaning a black hole is characterized only by its mass, spin, and charge, became famous. But more importantly, in his lectures around this time, he consistently used the term black hole. It was simple, vivid, and unforgettable. He deliberately popularized it, and the name spread like wildfire through the scientific press and into public consciousness. With a name, the concept gained tangible reality. The ghost had been christened. Now, armed with a robust theory and a powerful name, astronomers needed to find one. They knew what to look for. An invisible object with a mass too great for a neutron star, revealed by its gravitational grip on a visible companion or by the fierce glow of matter it was consuming. The hunt was on, and the prime suspect was already in the sights of a new generation of telescopes orbiting above the Earth's atmosphere. The theoretical stage was set. The name was coined. Now, the hunt required a new kind of vision, one that could see not with light, but with the energy of violence. The serene optical sky revealed only the placid surface of stars. To find a black hole, one had to listen for the screams of matter in its death throes, screams emitted in the X-ray part of the spectrum. Earth's atmosphere is a protective shield, absorbing the deadly X-rays from space. To see this violent universe, instruments had to ascend above it. The space age made this possible. In the 1960s and early 1970s, a series of pioneering X-ray telescopes were launched on rockets and satellites. They painted a shocking new picture of the cosmos. The sky was teeming with bright, variable X-ray sources, many of them in our own Milky Way galaxy. These were not gentle embers. They were cosmic blowtorches. Among the brightest and most famous of these sources was Cygnus X-1, discovered in 1964. For years, it was just a name, a coordinate, and a fluctuating X-ray signal. Its nature was a mystery. Was it a distant galaxy? A peculiar star? The key to unlocking its secret lay in precise localization. If astronomers could pinpoint its exact position with radio telescopes, they might identify a visible counterpart. In early 1971, radio astronomers using an interferometer network did just that. They located Cygnus X, one with unprecedented accuracy. Its position coincided with a known, unremarkable-looking blue supergiant star named HD 226868, about 6,000 light-years away. This was the breakthrough. Optical astronomers, swung their telescopes toward the star. Detailed spectroscopic observations revealed its secret. HD 226868 was not alone. It was wobbling. The star's light exhibited a periodic Doppler shift, its spectrum blue shifting and red shifting with a precise rhythm every 5.6 days. This was the telltale sign of a binary system. The visible star was orbiting an unseen companion. Using Kepler's laws of motion, astronomers could calculate the mass of that companion from the speed and period of the visible star's orbit. The results were startling. The unseen object had a minimum mass of about 9 times that of our Sun. This was the critical number. The theoretical maximum mass for a neutron star was believed to be around 2 to 3 solar masses. Beyond that, no known force could prevent collapse into a black hole. The companion's mass was 3 times higher than this limit. It could not be a neutron star. It could not be a white dwarf. It was too massive, too compact, and completely dark. The only plausible explanation, the only object that could fit the data, was a black hole. But science demands more than a plausible explanation. It demands a consistent story. The X-rays themselves provided the final chapter of that story. The blue supergiant HD 226868 is a massive, windy star. The black hole's immense gravity acts as a cosmic vacuum cleaner, pulling a stream of gas from its companion. This gas does not fall directly into the hole. Conservation of angular momentum causes it to spiral in, forming a vast, flattened, whirling disk around the black hole, an accretion disk. As the gas spirals inward, it is compressed and heated by ferocious friction. Temperatures in the inner regions of the disk soar to millions of degrees. Matter this hot does not glow in visible light. It glows in X-rays. The intense and variable X-ray signal from Cygnus X. One is the death cry of the stolen matter, superheated to incandescence, just moments before it crosses the event horizon and vanishes forever. The system is a perfect cosmic engine, a visible star feeding an invisible monster with the monster's meal ticket written in X-rays. The case was compelling. Yet, in the true spirit of science, it was met with healthy skepticism. Extraordinary claims require extraordinary evidence. Could there be another explanation? Perhaps the mass estimates were wrong. Perhaps there was a third star in the system complicating the measurements. Perhaps our understanding of neutron star physics was incomplete. The most famous expression of this skepticism became a legendary bet. In 1974, physicists Kip Thorne and Stephen Hawking wagered on the true nature of Cygnus X1. Thorne, confident in the interpretation, bet that it was a black hole. Hawking, playing devil's advocate and perhaps hedging against his own profound theoretical work on black holes, bet that it was not. The wager was symbolic, sealed with a playful subscription to a magazine. Hawking later said he bet against the black hole partly because he wanted the thrill of losing, and partly as an insurance policy. If black holes didn't exist, much of his life's work would be for nothing. Over the following decade and a half, the evidence became overwhelming. More precise measurements tightened the mass estimate. Observations of flickering X-rays on timescales of milliseconds confirmed the incredibly small size of the emitting region, smaller than the distance between Earth and the Moon, yet containing the energy of several suns. Only the deep gravitational well of a black hole could explain such power packed into such a tiny volume. In 1990, Stephen Hawking conceded the bet. He literally broke into Kip Thorne's office at Caltech and signed the bet paper, acknowledging defeat. The black hole had won its first great victory in the court of observational evidence. The discovery of Cygnus X was a paradigm shift. It transformed black holes from mathematical ghosts into standard inhabitants of our galaxy. Astronomers began finding other strong candidates, V404 Cygni, A0620-00, and many more. Each was a binary system with an unseen companion too massive to be a neutron star, each glowing with the hot X-rays of an accretion disk. But these were stellar mass black holes, the corpses of massive stars. The theory also predicted monsters of an entirely different scale. If a dying star could leave a black hole of 10 solar masses, what could a collapsing cloud of gas at the center of a galaxy create? The answer was emerging from studies of the mysterious, energetic hearts of distant galaxies. The black hole was not merely a stellar end product, it was a galactic architect. Its story was about to expand from the scale of stars to the scale of universes. The confirmation of stellar mass black holes like Cygnus X was a monumental leap, but it also opened a door to a grander, more terrifying possibility. If gravity could forge such traps from single stars, what could it create given millions or billions of stars worth of mass? The answer lay not in our galactic backyard, but in the furious, brilliant hearts of distant galaxies. For decades, astronomers had been puzzled by quasars. Discovered in the early 1960s, these quasi-stellar radio sources looked like faint blue stars, but had bizarre, high-energy spectra. Their true nature was revealed when their redshifts were measured. The redshifts were enormous, meaning quasars were not stars in our galaxy, but objects at the very edge of the observable universe. To be visible across such cosmic distances, a single quasar had to outshine an entire galaxy by a factor of 100 or 1,000. Yet this staggering energy was emitted from a region smaller than our solar system. No known nuclear process could explain it. The only conceivable engine powerful enough and compact enough was a supermassive black hole. Theorists like Yakov Zeldovic and Edwin Salpeter proposed a model in 1964. Imagine a black hole with the mass of 1,000,000 or 1,000,000,000 suns. Envision a vast whirlpool of gas, dust, and even entire stars swirling around it, forming an accretion disk of unimaginable scale. The gravitational energy released as this material spirals inward would be colossal, converting matter into radiation with ferocious efficiency. This would be the quasar engine, a supermassive black hole in a state of violent, gluttonous feeding. But quasars were distant, ancient phenomena, active in the early universe. Did such monsters still exist in the present day, quieter cosmos? The logical place to look was at the center of our own Milky Way. In the constellation Sagittarius, radio astronomers had identified a strong, compact source named Sagittarius A star. For years, it was just another radio blip. But as telescope resolution improved, a picture began to emerge. The key was to observe not the black hole itself, but the stars around it. If a supermassive black hole resided at the galactic center, the stars very close to it would be moving under its immense gravitational influence. They would orbit at blistering speeds. Starting in the 1990s, astronomers like Reinhard Genzel and Andrea Ghez began a decades-long project, using the world's largest telescopes and a technique called adaptive optics to cut through Earth's atmospheric blur. They tracked individual stars in the crowded galactic center, year after year. What they saw was a celestial ballet of breathtaking precision and speed. Stars like S2 followed sharp, elliptical orbits around an unseen focal point, Sagittarius A star. They reached speeds of over 5,000 kilometers per second at their closest approach, whipping around a dark center. By applying Newton's laws, just as with Cygnus X, one but on a vaster scale, they could weigh the invisible object. The result was definitive. Packed within a region smaller than the orbit of Mercury was a mass of about 4 million suns. The density was so extreme that no cluster of normal stars, neutron stars, or stellar black holes could explain it. The object had to be a single supermassive black hole. Our own galaxy, it turned out, harbored a sleeping giant at its heart. This discovery connected the dots. Quasars were the youthful, hyperactive phase of supermassive black holes. Galaxies like our own contained the same beasts, but now mostly quiet, having consumed the readily available fuel in their vicinity. The black hole was not a rare stellar oddity. It appeared to be a fundamental component of galaxy formation and evolution. Every large galaxy likely contained one that the narrative of the black hole had now completed a breathtaking arc. It began as a dark star in Newton's mind, became a mathematical ghost in Einstein's equations, was named by Wheeler, and was first caught in the act of stellar cannibalism with Cygnus X1. Now, it was recognized as a dormant titan, the silent gravitational anchor at the center of our island universe. From a theoretical curiosity, it had become an astrophysical cornerstone. Yet, for all this progress, the evidence remained indirect. We saw the frantic orbits of stars, the glow of hot gas, the shadows they cast. We inferred the presence of the whole from the behavior of things around it. The black hole itself remained shrouded, its most iconic feature, the event horizon, still a theoretical boundary. The desire to see that boundary, to resolve the shadow of the black hole against the glowing maelstrom around it, became the next great frontier. It would require turning the entire Earth into a telescope and looking with radio eyes at a wavelength that could pierce the intervening dust. That would be a story of global collaboration and audacious engineering. For now, as this chapter closes, consider the profound change in understanding that had taken place. In less than a century, humanity had gone from debating whether such objects could even exist to mapping the orbits of stars around one in our own galactic core. We had learned to see by listening to gravity's story. The invisible had been made tangible not by sight, but by inference, measurement, and the unwavering trust in the laws of physics. Let this thought comfort you as you drift toward sleep. The same gravity that holds you to your bed is the force that shapes the orbits of stars around a darkness 4 million times the mass of our sun, 26,000 light-years away. You are connected to that abyss by the most fundamental of forces. Its existence is no longer a question of if, but of how it shapes the cosmos around it. The monster is real, and we have found its lair. Begin a slow, 3-minute fade. The deep, pulsing heartbeat of the galactic core slows and deepens further, transforming into a profound, resonant silence, the sound of immense mass warping spacetime itself. This foundational tone holds, unwavering, before gradually dissolving into the quiet of the room. The discovery of Cygnus X-1 was a revelation, but it was not an isolated event. It was the first clear signal from a hidden population, proof that the universe was littered with these gravitational tombs. This chapter is the story of that population's emergence into the light of science. It is the story of how astronomers, armed with new senses that could see in X-rays and radio waves, began to map the ghosts in our cosmic neighborhood and beyond. The journey truly began with the development of X-ray astronomy. For centuries, astronomy was the study of visible light. But the universe is a multisensory experience, and visible light is only a narrow slice of the electromagnetic spectrum. High-energy X-rays, emitted by matter heated to millions of degrees, reveal the violent, chaotic, and explosive processes hidden from optical telescopes. The first cosmic X-ray source beyond the sun was discovered quite by accident in 1962. A team led by Riccardo Giacconi launched a sounding rocket equipped with Geiger counters to study X-rays from the moon. They did not find lunar X-rays. Instead, they discovered a powerful, uniform background of X-rays coming from all directions, and one brilliant, point-like source in the constellation Scorpius X-1. It was hundreds of times brighter in X-rays than the sun. This discovery marked the birth of X-ray astronomy and earned Giacconi a Nobel Prize decades later. Scorpius X-1 was later identified as a neutron star accreting matter from a companion, a less massive cousin to the black hole binary. It showed that compact objects in binary systems were potent X-ray emitters, setting the stage for the discovery of black hole candidates. The 1970s became the golden decade of X-ray discovery, thanks to satellites like Uhuru, the first dedicated X-ray observatory. Uhuru cataloged hundreds of sources, Among them were many like Cygnus X1, variable, high-luminosity X-ray sources associated with massive, visible stars. Each one was a potential black hole. The method became routine. Identify an X-ray source, find its optical counterpart, measure the spectrum of the visible star, detect its orbital wobble, calculate the mass of the unseen companion. If the mass exceeded 3 solar masses, it was a strong black hole candidate. V404 Cygni, discovered in 1989, became another textbook case. It is a binary system where a star slightly smaller than the Sun orbits a black hole of about 9 solar masses every 6.5 days. What made V404 Cygni special was its dramatic variability. It would slumber in quiescence for decades, then erupt in spectacular X-ray and optical outbursts as instability in the accretion disk triggered a sudden feast for the black hole. These outbursts provided a wealth of data, allowing scientists to study the physics of accretion in real time. Then there was a 0620-00, discovered in 1975 during a spectacular outburst that briefly made it the brightest X-ray source in the sky besides the Sun. In quiescence, it revealed a low-mass star orbiting a dark companion of about 6 solar masses. These systems, where a black hole feeds on a low-mass star, are known as microquasars. They act as miniature, nearby laboratories for studying the same processes that power distant quasars. With each new candidate, the catalog of stellar mass black holes in the Milky Way grew. They were no longer freaks of nature. They were a standard fossil record of the most massive stars. Estimates suggested there could be hundreds of millions of them scattered throughout our galaxy, silent and dark, unless they were actively feeding from a companion. But the story of ghost hunting was not confined to our galaxy, nor to stellar mass objects. The same X-ray and radio techniques began to probe the centers of other galaxies, revealing phenomena of unimaginable scale. The term active galactic nucleus, AGN, was coined to describe the energetic cores of galaxies that could not be explained by starlight alone. This category included quasars, but also safer galaxies, radio galaxies, and blazars. The unifying theory for all of them was the accretion of matter onto a supermassive black hole. Radio astronomy played a pivotal role. Many AGNs shot out colossal jets of plasma, stretching for thousands of light years, emitting strong radio waves. These jets were direct tracers of the central engine's power and orientation. The black hole's intense gravity and magnetic fields were somehow focusing and accelerating matter to nearly the speed of light, launching it into intergalactic space. The galaxy M87, a giant elliptical galaxy in the Virgo cluster, became the prime example. Its famous jet, visible even in small telescopes, was a cosmic signpost pointing directly to a supermassive black hole. To weigh these distant monsters, astronomers used a technique similar to that used on Sagittarius A*, but from much farther away. They observed the motion of stars or gas clouds in the very centers of other galaxies. The Hubble Space Telescope, launched in 1990, was instrumental. Freed from the blurring atmosphere, Hubble could resolve the dense star clusters at galactic centers. Spectroscopic measurements revealed stars whirling at incredible speeds, implying the presence of dark, massive objects. One by one, galaxies yielded their secrets. The giant elliptical galaxy M87 was found to harbor a black hole of about 6.5 billion solar masses. The Sombrero Galaxy contained one around 1 billion solar masses. It became clear that the mass of the central black hole was correlated with properties of the galaxy itself, particularly the mass of its central bulge of stars. This correlation suggested a profound coevolution. Galaxies and their central black holes were not independent. They grew together, each influencing the other's development. The black hole was not a passive occupant. It was a fundamental component of galactic anatomy. By the turn of the 21st century, the evidence was overwhelming and multifaceted. Stellar mass black holes revealed themselves through X-ray binaries in our galaxy. Supermassive black holes revealed themselves through the orbital dynamics of stars and galactic nuclei, and through the colossal energy output of AGN. The ghosts had been tracked, weighed, and measured. They were everywhere. Yet, for all this progress, a fundamental veil remained. All this evidence was circumstantial, however compelling. It was like condensing the presence of a powerful whirlpool in a dark sea by watching the frantic, circular paths of driftwood and debris around it. The goal now was to peer past the debris, to see the dark vortex itself, to image the shadow of the event horizon. That would require a telescope of impossible size and a new kind of astronomical vision. As the catalog of black hole candidates grew from a handful to dozens, a new scientific discipline was born: black hole astrophysics. It was no longer enough to simply discover them. Scientists wanted to understand their behavior, their demographics, and their profound influence on their surroundings. The ghosts were not just passive endpoints. They were dynamic engines that shaped the fabric of space-time and the evolution of galaxies. The study of X-ray binaries became a rich field. By analyzing the flickering, flaring, and spectral changes in the X-ray emission, physicists could probe conditions just outside the event horizon. One of the key predictions of general relativity for a black hole is the existence of an innermost stable circular orbit. This is the point where matter can no longer orbit peacefully and must plunge into the hole. Measuring the size of this orbit from the X-ray spectrum provides a direct estimate of the black hole's mass and spin. For the first time, scientists were not just weighing black holes from afar. They were mapping the warp space-time at their very edges. Some systems, like the famous microquasar JRS 1915 + 105, exhibited astonishing relativistic jets. These jets, moving at over 90% the speed of light, were scaled-down versions of the jets seen erupting from supermassive black holes in distant galaxies. Studying them provided real-time insights into how black holes can convert gravitational energy into directed cosmic ray beams. The mechanism is thought to involve twisted magnetic fields anchored in the swirling accretion disk, acting like a colossal slingshot that flings plasma outward along the black hole's rotation axis. Meanwhile, the search for supermassive black holes intensified. The correlation between black hole mass and galactic bulge mass was striking. But was it universal? Astronomers began hunting for black holes in smaller, dwarf galaxies and in galaxies without a classical bulge. They often found them, suggesting that perhaps most galaxies, regardless of size or type, host a central black hole as a standard feature of their formation. Some of the most compelling evidence came from water masers. In the dense, dusty disks of gas orbiting some galactic centers, water molecules act as natural amplifiers, producing bright, narrow radio emission lines. By mapping the precise Doppler shifts of these masers, astronomers could trace the rotation of the disk with exquisite precision. In Galaxy NGC 4258, a team using the Very Long Baseline Array measured a disk of water masers orbiting a central mass of about 40 million suns with Keplerian precision. The disk was warped, thin, and unmistakably centered on an invisible, supermassive object. It was one of the cleanest, most direct mass measurements of a supermassive black hole ever made, a gravitational signature etched in microwave radiation. But perhaps the most dramatic confirmation of the supermassive black hole's influence came from observing tidal disruption events. Occasionally, an unlucky star will wander too close to a galaxy's central black hole. The black hole's tidal forces, the difference in gravity between the star's near and far side, can overcome the star's own gravity and rip it apart. About half of the stellar debris is flung away, while the rest forms a temporary, brilliant accretion disk around the black hole, producing a months-long flare across the electromagnetic spectrum. These events are like cosmic burglar alarms, suddenly illuminating a dormant black hole and allowing astronomers to study its properties. They provided direct proof that these monsters, though often quiet, were always present and always hungry. All this evidence painted a consistent, yet still indirect, picture. The case for black holes was so strong that in 2020, the Nobel Prize in Physics was awarded to Roger Penrose for the theoretical discovery that black hole formation is a robust prediction of general relativity, and to Reinhard Genzel and Andrea Ghez for the experimental discovery of a supermassive compact object at the center of our galaxy. It was the ultimate scientific vindication. Black holes had moved from the fringes of theory to a cornerstone of modern physics, worthy of the highest honor. Yet, a profound distinction remained. The Nobel citation referred to a supermassive compact object. Even with mountains of evidence, the prize committee's language was meticulously precise. The orbits of stars proved the existence of an incredibly massive, incredibly compact dark object. General relativity said such an object must be a black hole with an event horizon. But had we actually seen the hallmark of a black hole, the event horizon, the point of no return? Not yet. The final, direct proof required seeing the shadow that a black hole casts against the bright glow of its accretion flow. That shadow is the silhouette of the event horizon, lensed and magnified by the black hole's own gravity. The challenge was immense. The angular size of a black hole's shadow on the sky is unbelievably small. For Sagittarius A*, is about 50 microarcsecons. To resolve, that is equivalent to seeing a donut on the surface of the moon from Earth, or reading the date on a coin in New York from London. No single telescope on Earth, not even the largest, could achieve such resolution. The solution was as ambitious as the goal itself. By synchronizing radio telescopes across the globe, from the high deserts of Chile to the volcanoes of Hawaii, from the mountains of Arizona to the South Pole, astronomers could create a virtual telescope the size of the entire planet. This technique is called Very Long Baseline Interferometry, VLBI. Combining the signals from these widely separated dishes simulates the resolving power of a single dish as large as the distance between them, an Earth-sized radio telescope. This was the Event Horizon Telescope project. Its primary targets were the two black holes with the largest apparent angular size, Sagittarius A* in our galactic center, and the far more massive black hole in the galaxy M87, which, due to its greater distance and mass, appears about the same size on the sky. For years, the EHT collaboration developed new hardware, sophisticated algorithms, and painstaking calibration methods. They needed to observe at a very short radio wavelength of about 1.3 millimeters to pierce the turbulent gas between us and the galactic center. They needed a perfect alignment of weather across multiple continents. They needed to record petabytes of data with atomic clock precision. They were attempting to take a photograph of a shadow at the edge of the universe, using the planet itself as their camera. The Event Horizon Telescope was more than an instrument. It was a global act of faith in theory and technology. The predictions were clear. General relativity, combined with models of hot, magnetized plasma, forecast what the shadow of a black hole should look like. It would not be a simple, dark circle. The black hole's immense gravity would bend light around it, creating a bright ring of photons orbiting just outside the point of no return. Within that ring would lie a darker region, the shadow, a lensed and magnified image of the event horizon itself. For a non-rotating black hole, the shadow would be a perfect circle. For spinning one, it would be slightly flattened on one side. The EHT collaboration scheduled observing runs for April 2017. For Sagittarius A*, they had a narrow window of only a few nights. The weather had to be perfectly clear and dry at all 8 participating sites simultaneously, from the Spanish Sierra Nevada to the Antarctic South Pole Telescope. The stakes were immense. They were attempting to capture a portrait that had been forming in the human imagination for a century, from Schwarzschild's equations to Wheeler's naming. The data collected was staggering in volume. Each telescope generated so much information that it could not be streamed over the internet. The hard drives, filled with atomic clock time data, were physically flown to central processing facilities at the MIT Haystack Observatory and the Max Planck Institute for Radio Astronomy in Germany. The process of correlating the data, filtering out noise, and reconstructing an image took nearly 2 years. It was a painstaking puzzle with petabytes of pieces. On April 10, 2019, the world watched as the EHD collaboration held simultaneous press conferences on multiple continents. They revealed the first direct image of a black hole. It was not Sagittarius A*, our own galactic monster, whose image proved more difficult to reconstruct due to rapid variability. The historic first image was of the supermassive black hole at the heart of the galaxy Messier 87, 55 million light-years away, and weighing 6.5 billion suns. The image was instantly iconic. There it was, a bright, asymmetric ring of fire, and at its center, a dark shadow. It matched the predictions of general relativity with uncanny precision. The dark central region was the shadow of the event horizon, roughly 2.5 times larger than the actual event horizon due to gravitational lensing. The bright ring was the photon capture orbit, the last path light could take before falling in. The asymmetry in the ring's brightness confirmed the black hole's spin and the direction of its swirling accretion flow. The scientific impact was immediate and profound. The image provided the most direct evidence yet for the existence of black holes. It was not an inference from orbits or a measurement of mass. It was a picture of the thing itself, or more precisely, of its gravitational prison. The size and shape of the shadow allowed for precise tests of general relativity in an extreme regime. No deviations from Einstein's predictions were found. The monster's silhouette was exactly as foretold. For the public, the image was a marvel. It made the abstract concrete. The black hole was no longer a scientist's sketch or a supercomputer simulation. It was a real object in a real galaxy, captured by human ingenuity. It represented the culmination of a century-long journey from equations to evidence. The work did not stop with M87. The EHD continued to observe. In May 2022, they unveiled the long-awaited image of Sagittarius A*. It showed a remarkably similar structure, a bright, lumpy ring with the central dark shadow, though appearing more turbulent due to the faster-changing environment around our galaxy's less voracious black hole. Seeing our own local monster confirmed that the physics was universal. The same rules govern black holes from a few million to billions of solar masses. With these images, the hunt for ghosts reached a new plateau. The indirect evidence, orbits, X-rays, jets, disruptions, had been overwhelmingly convincing. Now humanity had direct visual proof. We had seen the shadow of the unseen. The journey that began with a question about escape velocity had arrived at a portrait of oblivion. This knowledge changes our place in the cosmos. We live in a galaxy centered on a silent titan whose shadow we have now mapped. We understand that such titans reside in the hearts of most galaxies, shaping their growth. We know that stellar mass black holes are scattered through the galactic disk, the remains of dead giants. The universe is not just full of stars and planets. It is also punctuated by these sinks of gravity, fundamental to its architecture. As you listen now, let the weight of this achievement bring not fear, but a profound sense of clarity and connection. The same laws of physics that predict a black hole's shadow govern the fall of an apple and the orbit of Earth. Human curiosity, armed with mathematics and technology, has stretched across 55 million light-years to confirm a prediction made in a war-torn Europe over a century ago. We have looked into the darkest possible place and found that it obeys our equations. In a universe that can seem chaotic, this is a deep, resonant harmony. The story of black holes is no longer one of mystery, but of understanding. The ghosts have been measured, weighed, photographed, and understood. They are a testament to the power of the human mind to comprehend the extremes of creation. As you drift toward sleep, picture that faint, fiery ring in the void, a lighthouse in the dark marking the edge of physics. It is there, and because we can see it, we know we are home in a cosmos we can comprehend. For centuries, astronomy was the science of light. We mapped the cosmos by collecting photons, particles of light, across the electromagnetic spectrum, from radio waves to gamma rays. Every discovery, from Galileo's moons to the black hole shadow, came to us on waves of light. But light has limitations. It can be absorbed, scattered, or obscured by dust and gas. It shows us the universe's surface. To perceive the deepest, most violent events, where space and time themselves are wrenched and shaken, we needed a new sense. We needed to learn how to listen. The story of this new sense begins, once again, with Albert Einstein. In 1916, shortly after publishing his theory of general relativity, Einstein realized a profound consequence of his equations. Just as accelerating electric charges produce electromagnetic waves, accelerating masses should produce ripples in the fabric of space-time itself. He called these ripples gravitational waves. They would travel at the speed of light, stretching and squeezing space as they passed. But Einstein was skeptical they could ever be detected. The distortions they produced would be vanishingly small, far smaller than the width of an atomic nucleus over a distance of kilometers. He later waffled, even publishing a paper suggesting they might not exist at all. For decades, the question of gravitational waves remained a theoretical curiosity, a subtle mathematical footnote to the grand theory of curved space-time. The first person to take their physical reality seriously was Joseph Weber. In the 1960s, Weber built the first gravitational wave detector. It consisted of large, solid aluminum cylinders, or bars, suspended in vacuum chambers. The idea was that a passing gravitational wave would minutely stretch and compress the bar, exciting vibrations that could be measured with piezoelectric sensors. Weber claimed to have detected signals, but his results could not be replicated by other groups. The scientific community grew skeptical. The hunt for gravitational waves earned a reputation as a fringe pursuit, a graveyard for careers. But the theoretical foundation was solid. In the 1970s and 80s, indirect evidence mounted. Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. By meticulously timing the pulses from one of them, they observed that the stars were spiraling inward at exactly the rate predicted if they were losing energy by emitting gravitational waves. It was a brilliant, indirect confirmation. They won the Nobel Prize in 1993. Gravitational waves were real. The challenge was to build an instrument sensitive enough to feel their direct whisper. That instrument would not be a bar, but an interferometer. The concept was elegant. Imagine a laser beam split into two perpendicular paths, each traveling down a long vacuum tube to a mirror several kilometers away. The beams reflect back and recombine. In normal conditions, the light waves are tuned to cancel each other out through destructive interference. But if a gravitational wave passes, it will momentarily change the length of one arm relative to the other. One path becomes minutely longer, the other minutely shorter. This destroys the perfect cancellation, allowing a flicker of light to reach a photodetector. The signal is a measure of the change in distance between the mirrors. To detect a change 10,000 times smaller than a proton required engineering of almost unimaginable precision. This was the vision of LIGO, the Laser Interferometer Gravitational Wave Observatory. Its champions, like Kip Thorne, Rainer Weiss, and Ronald Drever, fought for decades to turn the vision into reality. They faced skepticism, funding battles, and immense technical hurdles. They had to isolate the mirrors from every conceivable vibration, distant traffic, ocean waves, even the random motion of molecules in the mirror coatings. The final facilities, built in the remote deserts of Hanford, Washington, and Livingston, Louisiana, were marvels of quiet. Each housed an L-shaped interferometer with arms 4 kilometers long, the most sensitive measuring devices ever constructed. Initial operations began in 2002. For years, they detected nothing but silence and terrestrial noise. The advanced LIGO upgrade, completed in 2015, was the crucial leap. With improved lasers, mirrors, and vibration isolation, its sensitivity was increased tenfold. It could now probe a volume of the universe 1,000 times larger. The stage was set. The universe, it seemed, was waiting for the new ears to open. On September 14th, 2015, at 9:50 and 45 seconds Universal Time Coordinated, a signal arrived. It hit the Livingston detector first. 7 milliseconds later, it hit Hanford. The signal was clean, strong, and unmistakable. It began at a low frequency of 35 Hz, a deep cosmic hum. It then rapidly swept upward in frequency and amplitude over 1/5 of a second, ending in a final, characteristic chirp before cutting off. The waveform was a perfect match for the final moments of two massive objects spiraling together and merging. Calculations showed the objects were about 29 and 36 times the mass of our Sun. The merger produced a single object of about 62 solar masses. The missing mass, 3 suns worth, had been converted into pure energy and radiated away as gravitational waves. This event, dubbed GW150914, was the merger of two black holes over 1 billion light-years away. The detection was not announced until February 2016, after months of exhaustive verification. The team had to rule out every possible false alarm, a software glitch, a deliberate test signal, an earth tremor. The signal passed every test. It was real. When the announcement came, the scientific world erupted. A new window on the universe had been thrown open. We were no longer just astronomers. We had become listeners to the symphony of space-time. The detection of GW150914 was more than a triumph of engineering. It was a direct encounter with pure gravity in its most violent expression. For the first time, humanity had felt the fabric of space-time tremble. The signal carried specific, revealing information. The increasing frequency of the chirp corresponded to the black hole's ever-quickening orbit as they lost energy. The amplitude told of their immense masses. The final, clean cutoff marked the moment they merged into a single, quiescent black hole. The absence of any subsequent electromagnetic flash was also telling. This was a dark event, two invisible objects colliding in a void, observable only through the ripples they made in space-time itself. The LIGO data allowed physicists to perform unprecedented tests. They compared the observed waveform with billions of computer-simulated templates based on Einstein's equations. The match was perfect. General relativity, a century after its conception, had passed its most extreme test. They could also infer properties of the final black hole, like its spin and its ring down. The brief period where it shed distortions like a bell ringing after being struck. Everything fit. The discovery inaugurated the field of gravitational wave astronomy. It proved that binary black hole systems not only existed, but were common enough to be detected. The black holes in GW150914 were also more massive than any known stellar mass black hole in our galaxy, hinting at a previously unknown population. The universe was speaking in a new language, and it was telling stories of dark, heavy things crashing together in the deep cosmic past. LIGO, now joined by its European counterpart Virgo in Italy, continued to listen. The detections began to flow. GW151226, another black hole merger. Then, on August 17, 2017, an alert went out that would change everything. The signal, named GW170817, was different. It was longer, less massive, and crucially, it was followed 2 seconds later by a flash of gamma rays detected by the Fermi and integral satellites. This was the signature of a neutron-star merger. The gravitational wave signal pinpointed a region of sky. Within hours, optical telescopes swiveled to that patch and found a new, bright point of light in the galaxy in GC 4993, about 130 million light-years away. It was a kilonova, an explosion powered by the radioactive decay of heavy elements forged in the neutron-rich debris of the collision. For weeks, observatories across the globe and in space trained every instrument they had on this event. They saw the afterglow across the spectrum, from X-rays to radio waves. They detected the signature of newly created gold, platinum, and other heavy elements, solving the long-standing mystery of where about half the elements heavier than iron in the universe come from. This single event united gravitational wave astronomy with every other branch of astrophysics. It was the first multi-messenger observation of a cosmic cataclysm. But the black hole mergers kept coming, each with its own tale. Some involved black holes spinning rapidly, almost aligned with their orbit. Others had misaligned spins, suggesting a turbulent formation history. Some mergers produced black holes so massive they fell into the elusive intermediate mass range, a possible missing link between stellar and supermassive black holes. Each chirp was a fossil record of a binary system that survived the deaths of 2 massive stars, orbited for billions of years, and finally succumbed to gravitational radiation. The data began to paint a statistical picture. Binary black holes are not rare. LIGO and Virgo now detect them roughly once a week during observing runs. This implies that across cosmic history, the universe has been filled with the silent, invisible drumbeat of colliding dark giants. We are mapping a hidden landscape of gravity, a landscape invisible to light. The gravitational wave signals also offer a new, direct way to measure cosmic distances. The amplitude of the wave tells us how much space-time was stretched, which relates to the energy of the source and its distance. This provides a standard siren, a new kind of cosmic yardstick independent of the traditional cosmic distance ladder based on stars and galaxies. By combining standard sirens with other measurements, scientists can probe the expansion rate of the universe and the nature of dark energy with fresh precision. Perhaps most philosophically, gravitational waves deliver a pure dose of gravity unmediated by matter. Light is emitted by excited atoms or charged particles. It interacts with matter along its journey. Gravitational waves are emitted by the motion of mass itself and travel through the universe nearly unimpeded. They are gravity communicating with itself. Listening to them is as close as we can get to hearing the raw geometry of the cosmos. As the network of detectors grows, with Kagra in Japan and LIGO India planned for the future, our hearing will become more acute and directional. We will locate sources more precisely and detect fainter, more distant events. We will listen for the steady hum from countless unresolved binaries, a gravitational wave background that permeates space-time. We may even detect the waves from the cosmic inflation epoch, a whisper from the first fraction of a second after the Big Bang. The act of listening has transformed our relationship with the universe. We are no longer passive observers of a silent cinema of light. We are participants in a dynamic, vibrational cosmos where space itself rings like a drum. Each chirp from 1 billion light years away is a confirmation that the universe is alive with motion and change on the most fundamental level. The opening of the gravitational wave window has done more than add a new channel to our cosmic senses. It has fundamentally altered the questions we can ask and the stories we can tell about the universe. Each ripple detected is a direct telegram from a catastrophic event, carrying encoded information about masses, spins, distances, and the very nature of gravity. We are now not just mapping where black holes are, but listening to how they move, dance, and unite in the dark. One of the most profound revelations from this new data concerns the birth of black holes themselves. The detection of black holes weighing tens of solar masses, like those in GW 150914, challenge existing models of stellar evolution. How do stars leave behind such heavy corpses? Theories now point to low metallicity environments in the early universe, where massive stars lose less mass through stellar winds, allowing their cores to remain ponderous until collapse. Other detected pairs have unusual spin orientations, suggesting they may have formed not from a binary star system that lived and died together, but through dynamic capture in dense stellar environments like globular clusters. Gravitational waves are giving us a census of black hole demographics, revealing populations that were hidden from electromagnetic astronomy. The future of this listening science stretches out in thrilling directions. Current ground-based detectors like LIGO and Virgo are sensitive to frequencies from about 10 Hz to several kilohertz, the domain of stellar mass compact object mergers. To hear the lower frequency waves from even more massive systems, we must go to space. The Laser Interferometer Space Antenna, LISA, is a planned European Space Agency mission. It will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, connected by laser beams. Free from seismic noise and with arm lengths measured in millions of kilometers, LISA will tune into the millihertz band. This frequency range is the domain of the cosmic giants. LISA will hear the slow, spiraling dance of massive black hole binaries in the centers of merging galaxies, years before they finally collide. It will detect the whispers from thousands of tight binary white dwarfs in our own galaxy. It may even sense the gravitational ripples from the earliest moments of the universe, a primordial background. LISA will allow us to trace the growth of supermassive black holes across cosmic time, listening to the soundtrack of galaxy assembly. There are even more speculative frontiers. Some theories of quantum gravity or string theory predict subtle deviations from Einstein's predictions in the strongest gravitational fields, perhaps in the ring-down phase of a black hole merger, or in the existence of exotic objects like boson stars or gravistars. As our detectors become more sensitive and our catalog of events grows into the thousands, we will search for these tiny deviations in the data. Gravitational waves may provide our first experimental hints of physics beyond general relativity, a glimpse into the quantum nature of spacetime itself. But perhaps the most immediate impact is the one felt in the human spirit. For millennia, we looked up at a silent, static sky. Then we learned to see its light. Now we have learned to feel its vibrations. The detection of a gravitational wave is a tactile experience for our species. It is the universe pushing and pulling at the very framework of our reality. That subtle chirp, processed from kilometers of laser beam and vacuum tube, is a handshake across 1 billion light years, a confirmation that we are not just observers, but participants in a dynamic, evolving cosmos governed by knowable laws. As you listen now, in the quiet of your own space, consider this. The space that surrounds you is not a static void. It is a dynamic medium, capable of stretching and compressing. 1 billion years ago and 1 billion light years away, 2 black holes ended their cosmic dance in a final embrace. The waves from that event have been traveling through the stretching fabric of the expanding universe all this time. They passed through our planet on September 14th, 2015. For 1/5 of a second, they shifted the mirrors in Louisiana and Washington by a distance smaller than a proton. That shift was captured, decoded, and understood. We felt that ancient collision. This knowledge connects you to the most violent events in the universe in a direct, physical way. The same space-time that you inhabit, that gives dimension to your room and rhythm to your breath, is the very thing that trembled with that signal. You are not separate from the cosmos. You are embedded in its fabric, and now that fabric speaks to us. Let this realization be a source of deep tranquility. The universe operates by rules so precise that we can predict the ripple from a collision of invisible masses 1 billion light years away, and then build machines to catch that ripple. There is order in the chaos, harmony in the violence. The same gravity that gathered the planets and governs the fall of leaves also orchestrates these immense, distant symphonies. The story of black holes is no longer confined to theory or indirect inference. It is written in the vibrations of space-time, a story we are now literate enough to read. We have moved from hunting ghosts to feeling their footsteps. We have mapped the darkness not with light, but with its absence, not with sight, but with touch. So as you drift toward sleep tonight, imagine not just the silent, dark objects out there, but the ripples they create. Imagine space as a still pond, and each black hole merger as a stone dropped in, sending circles out across the cosmic expanse. We have built our delicate instruments on the shore, and we are now counting the ripples, learning the history of every stone. The pond is vast, and the ripples are many, and we are listening. We have followed the black hole from a thought to an equation, from a name to a gravitational tremor. We have weighed them by the orbits of stars and heard them collide across 1 billion light-years. Yet, a fundamental human desire remained unfulfilled to see, to lay eyes upon the manifest edge where space and time lose their meaning, to transform the inferred shadow into an image. This final chapter is the story of that seeing. It is the story of how humanity built an eye the size of a planet to photograph the unphotographable. The target was known. At the heart of the giant elliptical galaxy Messier 57, 55 million light-years away, lurked a gravitational titan, designated M87*. This supermassive black hole was calculated to weigh 6.5 billion times the mass of our Sun. Its event horizon, though unfathomably large, was at an immense distance on the sky. It would appear as a tiny ring, about 40 microarcseconds in diameter. To resolve such a detail required a telescope with a resolution 10,000 times greater than the Hubble Space Telescope. No single dish on Earth could achieve this. The laws of physics dictate that the resolving power of a telescope depends on the size of its aperture relative to the wavelength of light it observes. To see M87* required a radio telescope with an aperture comparable to the diameter of Earth itself. This was the audacious goal of the Event Horizon Telescope collaboration. They would not build one giant dish. Instead, they would synchronize existing radio telescopes across the globe, from high mountain peaks to frozen deserts, creating a virtual telescope the size of our planet through a technique known as very long baseline interferometry. The concept is deceptively simple in theory, heroic in execution. Radio waves from the black hole arrive at each participating telescope at slightly different times. By recording the precise arrival time of the wavefront at each site using atomic clocks and later combining the data, scientists can synthesize the image that a single Earth-sized dish would have seen. The HD did not use one wavelength, but a specific band around 1.3 millimeters. This short radio wavelength could pierce the hot gas and dust surrounding the black hole, and its size was just right to balance resolution and the ability to penetrate Earth's atmosphere. The team selected sites that were high, dry, and geographically dispersed. The Atacama Large Millimeter Array in Chile, the IRM 30-meter telescope in Spain, the Large Millimeter Telescope in Mexico, the James Clerk Maxwell Telescope, and the Submillimeter Array in Hawaii, the South Pole Telescope in Antarctica, and the ALMA prototype antenna in Arizona. Weather was the enemy. They needed clear, stable atmospheric conditions at every single site simultaneously. The observing window for M87* in April 2017 was narrow. The logistics were a masterpiece of global coordination. Each telescope recorded petabytes of raw data onto custom-designed, helium-filled hard drives. The data was too vast to transmit electronically. The drives were physically flown, sometimes from the most remote locations like the South Pole, to central correlator facilities at the Max Planck Institute in Germany and MIT Haystack Observatory in the United States. The journey of the data was as epic as the observation itself. Then began the years-long process of correlation and analysis. The raw data was not a picture. It was a set of complex interference patterns between every possible pair of telescopes. Translating this into an image was an inverse problem with infinite possible solutions. The team developed sophisticated algorithms and tested them on simulated data. They split into multiple, independent teams who worked in isolation to reconstruct the image, a safeguard against bias. They were detectives with a planet-sized clue, reconstructing a scene from fragments of a shattered mirror. For 2 years, the secret was held by hundreds of scientists across the globe. They lived with the knowledge that in their hard drives might lie the first direct visual evidence of a black hole's event horizon. The pressure was immense. The potential for error or artifact was high. They calibrated and recalibrated, simulated and tested. The signal had to be teased from a universe of noise. What were they hoping to see? The predictions of general relativity were clear. A black hole against a bright background of hot, swirling gas should appear not as a solid dark circle, but as a dark shadow surrounded by a bright, asymmetric ring. The ring is light from the accretion disk, bent by the black hole's extreme gravity into a path that orbits the hole multiple times before escaping. This gravitational lensing creates a photon ring. The darkness within is the shadow of the event horizon, magnified by the lensing effect to about 2.5 times its actual size. The ring would be brighter on one side if the accretion disk was rotating, due to the relativistic beaming of light from the approaching side. On April 10, 2019, the world was shown what they had found. In coordinated press conferences across multiple continents, the EHT collaboration unveiled the image. There it was, a bright, fiery, asymmetric ring of light, and at its center, a dark, circular shadow. It was instantly recognizable. It was the face of M87 star. It was the shadow of the event horizon. The image was not just a confirmation. It was a measurement. The size and shape of the shadow allowed scientists to precisely calculate the black hole's mass, independently confirming earlier estimates. It provided a new, direct test of general relativity in a regime of extreme gravity. The theory passed perfectly. The shadow was exactly the size and shape Einstein's equations predicted. The monster silhouette, cast against the glow of its own furnace, matched the blueprint drawn a century before. The release of the M87 asterisk image was a global moment of collective awe, but for the Event Horizon Telescope collaboration, it was also a prelude. An even more challenging target awaited in our own cosmic backyard, Sagittarius A, the supermassive black hole at the center of the Milky Way. While M87 was a behemoth at a great distance, SGRA* was a relative featherweight, a mere 4 million solar masses, but it was 25,000 times closer. By a remarkable coincidence of cosmology, both black holes appeared as roughly the same size on our sky, about 50 microarc seconds. They were the two largest black holes in the angular sky. Photographing SGR-A* presented a unique and formidable set of challenges. Its proximity was a curse as much as a blessing. It resides in the crowded, dusty plain of our galaxy. Observing it required looking through a fog of interstellar gas and dust, which scatters and blurs radio waves. More critically, SGR-A* is dynamic. The gas swirling around it is turbulent and changes on timescales of minutes, unlike the more placid, larger-scale flow around M87. Trying to image SGR was like trying to take a sharp photograph of a playful kitten by using a camera with a multi-day exposure. The target would not sit still. The EHD had collected data on SGR-A* during the same April 2017 observing run. The same hard drives that carried the signal of M87* also carried the flickering whisper of our own galactic center. But the path to an image was far more tortuous. The standard imaging algorithms that worked beautifully for the steady M87* produced only a blurry, evolving smudge for SGR-A*. The team had to innovate. They developed new computational tools and techniques. They could not capture a single snapshot in time. Instead, they had to reconstruct a movie, a representation of the average structure that persisted beneath the rapid flickering. They used machine learning to generate millions of possible images consistent with the sparse EHD data, and then found the common features that appeared in all of them. It was an exercise in statistical inference on a cosmic scale. The effort took 3 additional years. Finally, on May 12, 2022, the EHD unveiled the image of Sagittarius A. There it was, a familiar, yet deeply personal sight. A bright, lumpy ring with a central dark shadow. The ring was not as smooth and symmetric as M87's. It showed bright knots and blobs, evidence of the turbulent, magnetized plasma swirling around it at near light speed. But the dark shadow was unmistakable. The portrait was grainier, but it was ours. It was the monster at the heart of our home galaxy, the silent pivot around which hundreds of billions of stars, including our sun, slowly revolve. Seeing SGR-A* completed a profound scientific and philosophical circle. For decades, we had tracked stars like S2 whipping around an invisible point at speeds that demanded a dark, massive object. Now we had seen the object itself, or rather, its gravitational silhouette. The orbits of the stars pointed like arrows to the shadow in the image. Indirect evidence and direct vision converged into a single, undeniable truth. The scientific yield from these two images is immense. They provide the most direct evidence possible for the existence of black holes. They test general relativity in the strong field regime, a place where space-time curvature is at its most extreme. So far, Einstein's theory has passed with flying colors. The size of the shadows rules out alternative compact objects like boson stars or gravistars that do not have a true event horizon. The images also probe the complex physics of accretion and jet launching. The asymmetry of the rings confirms that the accretion disks are rotating, and the observed brightness patterns inform models of magnetic fields and plasma physics in these extreme environments. For M87*, the image connects directly to the famous 1,000-light-year-long jet erupting from the galaxy's core. The EHT can see the base of that jet, the point where the black hole's gravity and spin focus and accelerate matter into a narrow, relativistic beam. But beyond the physics, the images achieve something else. They make the abstract concrete for the human mind. A black hole is no longer just a set of equations, a calculated mass, or a simulated ripple. It is a thing you can point to. You can look at the image and say, that dark region, that is a place from which no light returns. That bright ring is the last orbit of light. The image satisfies a deep-seated need to see in order to believe, even as science had already believed for decades based on overwhelming indirect evidence. The journey to this moment spans the entire history of our understanding of gravity. It began with Newton's universal law and the concept of escape velocity. It passed through Einstein's geometric revolution and Schwarzschild's singular solution. It endured decades of skepticism and mathematical exploration. It gained a name from Wheeler, found its first physical evidence in Cygnus X1, was heard colliding by LIGO, and was finally seen by a planet-sized telescope. Each step was built upon the last, a cumulative edifice of human curiosity and ingenuity. The black hole has been transformed from a terrifying paradox, a destroyer of information and physics, into a laboratory. It is a tool for testing our most fundamental theories, a key to understanding galaxy evolution, and a lens through which we observe the most extreme conditions the universe can produce. We have not solved all its mysteries, the singularity, the information paradox, the union with quantum mechanics, but we have moved it from the realm of pure speculation into the realm of observational science. As we stand now, gazing at these images from 2019 and 2022, we are not at an end, but at a new beginning. The first photographs of black hole shadows are not final answers. They are the opening of a new eye. The Event Horizon Telescope continues to grow, adding more telescopes, observing at new wavelengths, and increasing its sensitivity. Future images will be sharper. They may become movies, showing the turbulent flow of plasma around SGRA* in real time. They may reveal the intricate structure of the photon ring, a series of nested subrings predicted by theory, each corresponding to light that orbited the black hole multiple times before escaping. This would be a direct map of the warped geometry of spacetime. The story of the black hole is now woven into the larger tapestry of cosmic exploration. It intersects with the search for dark matter and dark energy. It is crucial to understanding the growth of galaxies across cosmic time. It pushes the boundaries of quantum gravity. The humble dark star of John Michel has become a central character in the narrative of the universe. But let us bring this story home, to this quiet moment to you. You have journeyed from an 18th century thought experiment to a 21st century photograph. You have followed the stubborn persistence of scientists who believed in the predictions of their mathematics, even when the objects seemed impossible. You have witnessed the evolution of a concept from heresy to fact. This knowledge offers a unique form of peace. In a world of constant change and surface noise, the black hole represents a profound, silent certainty. It is a manifestation of physical law in its purest, most extreme form. The same gravity that gives you weight governs the orbit of stars around an invisible point and carves a shadow of nothingness in a whirlpool of light. The universe operates by rules. We can understand them. We have understood this. So tonight, as you prepare for sleep, do not let the vastness of these ideas overwhelm you. Let them ground you. You are a conscious being on a small planet, orbiting an ordinary star, in the quiet suburbs of a spiral galaxy. At the center of that galaxy is a silent, dark sphere, a gravitational knot in space-time. We have seen its shadow. We have heard its collisions. We know it is there. This knowledge does not make the universe stranger. It makes it more familiar. We have mapped another part of our home. Close your eyes. Feel the gentle, unwavering pull of Earth's gravity holding you to your bed. That force, so quiet and constant, is a whisper of the same power that shapes galaxies and forges shadows in the void. You are connected to the black hole not by fear, but by understanding. You are part of a species that has reasoned its way to the edge of oblivion and looked calmly into the dark. The quest that began with a question about light and escape velocity has reached a sublime conclusion. We set out to find a ghost, and we have returned with its portrait. We sought to prove an idea, and we have instead opened a new sense. The black hole is no longer a monster in the dark. It is a known quantity, a subject of study, a wonder of nature. We have brought it into the light of human comprehension. Now release the images. Let the equations fade. Allow the stories of Chandrasekhar and Wheeler, of Penrose and Genzel, of the LIGO technicians and the EHD engineers, to settle into the quiet history of discovery. What remains is the simple, magnificent fact. The universe contains these things, and we found them. Our minds can reach across light years and map the unmappable. This is the true legacy of the hunt, not just a picture, but the proof of what we can do. As you drift into sleep, imagine not the terrifying abyss, but the brilliant ring of light around it. That ring is a beacon, a lighthouse built by gravity itself, marking the boundary of the known. Inside is mystery. Outside is everything we see, measure, and love. You are on the outside, in the realm of light and life. The shadow is there, but it is contained, understood, and beautifully, mathematically precise. Let that precision be your lullaby. The cosmos is vast, but it is not chaotic. It is deep, but it is not unknowable. You are resting in a universe that obeys rules, rules that we have learned to read. Sleep now, in the quiet confidence that comes with seeing the dark and knowing its name. Good night.